So continuing from the previous section, this video is about plotting frequency response. So in function of a frequency with the magnitude and phase in a separate plot. So for example, dV versus a logarithm scale of the frequency omega 2 pi f. In decibel dV is 20 based on log m. M is the magnitude. We'll go through that first and then we'll move on to polar plot next. Let's try to find the analytical expression for the magnitude of frequency response and the phase of frequency response for a system. G of S equal 1 over S plus 2. This is something that you're familiar with. We will plot both the separate magnitude and phase diagram and then a polar plot of it. This is example 10.1 from textbook NEECE. Solution for G of S equal 1 over S plus 2. First step, you substitute S with a J omega. So G of S now is G of J omega. And you replace wherever you see S with a J omega. So it is 1 over, within the bracket, the denominator is J omega plus 2. What it is translate into that. And the magnitude, so we'll go from here to here and shortly on the side. Magnitude of G of J omega we'll call M of omega, which is 1 over square root of omega squared plus 4. And phi of omega is, the phase is 810, or minus 10 to the minus 1, minus of arctant of omega over 2. And then you would plot G of omega equal M of omega with the phase angle phi of omega for all possible omega. So literally frequency sweep from 0 all the way to reasonable numbers. 1 hertz, 10 hertz, 100 hertz, kilohertz, 10 kilohertz, 100 kilohertz, megahertz, and so on. Let's do quick math. 1 over J omega plus 2. That is the same as 1 over J omega plus 2. 2 minus J omega. 2 minus J omega. So what happened is, on the top is 2 minus J omega. And then the bottom, if you kind of look at it, the same thing. This is same as 2 plus J omega. You have A plus B multiplying by A minus B is A squared plus BA minus AB minus B squared. So A squared plus AB minus AB minus B squared. So these cancels out, so it becomes 2A squared minus B squared. So that is the same thing. So this is A and this is B. A squared will be 2 squared minus B was a J omega squared. So you end up with 2 minus J omega over 2 squared is 4 minus J squared omega squared. And then remember, J squared is minus 1, or square root of minus 1 is J. So you end up having 4 minus 1 omega squared, which is a 4 plus omega squared. So you end up having 2 minus J omega over 4 plus omega square. That is the same as 1 over j omega plus 2. Because you're multiplying both sides the same thing, top and bottom. You're literally multiplying the whole system by 1. Okay, so you saw the math, and then now let's plot um, g of omega with all possible omega. That's how it looks like in a frequency response plot in polar. So this is omega, and all in radians per second. And one more calculation here, m over omega. That is pretty much 1 over j omega. So omega square plus 2 square and square root of it. That is coefficient of j, and then that is uh, what's right there. So frequency response plot in polar looks like this. I'm not going to ask you to draw it. All it's showing is that omega is varying from 0 all the way and then to here. And so back to this frequency response plot in polar. So pretty much you can kind of see where 1 rad per second is. Um, and you can find it. It's a 20 log 0.35. It's literally minus 9.12 dB. It's kind of not as intuitive to read, but all it's showing is it's been plotting all the possible places that would have these frequencies, radian per second. So remember, this was 1 over s plus 2. So for 1 over 1 over s plus 2 at s equal 2, I mean rad per second, um, omega is, not s is, that is right here at minus 45, and if you look at it, that's 1, 2, so right here, and that is at minus 45 shift, and that is of your interest, and it's happened to be the magnitude is if you think of it, so 10 to the minus 7 over 20, or minus 7 dB down, and happen to be this. The minus 7 dB down, how do you know? It's just around here in the right this point on your 20 log. So for the skill assessment 10.1, that's also in our worksheet, we'll try to find the analytical expression for the magnitude and phase response of this system, G of S being 1 over S plus 2, S plus 4. We'll skip making plot for the magnitude and phase using log frequency red ordinate because you need a plotter, and we'll also skip the polar plot of it. So we'll just find analytical expression that will be part of your final exam working with the Bodier plot only. I would have paused and tried myself, or you should have tried yourself, but this is the full solution for the analytical solution portion. So G of S, this was given s plus 2, s plus 4 being in denominator. What do you do? Step 1, you replace everything, all the s's, these, with j omega. So you will end up with g of j omega being this. So I'll show the steps. So it will be, I'm going to write on the side right here, 1 over j omega plus 2 times j omega plus 4. So 1, 2, 3, 4. So that will be j omega square, 1. Then the second one will be plus 4j omega, and this will be 3 plus 2j omega. Those are steps, not actual. And then step 4, that will be plus 2 times 4. So you end up with that is a denominator. I'll put it as denominator in forms of j omega square plus 6j omega plus 8. What is a j omega square? It's a j square omega square. That is minus 1 and omega square. So when you do the denominator, when you're multiplying those, denominator with j omega, well, it will be 8 plus 6j omega plus j square omega square. So you end up with square plus j6 omega. I can rewrite it. So you end up with 8 plus omega square plus j6 omega. Note what happened to this j square equal 1. Isn't square root of 1 j? So you can find out to 1. So square root of minus 1 is j. The j square is square root of minus 1 square. So that is minus 2. So I think this should be minus. So your magnitude is the real axis, real portion and imaginary portion, that square plus omega 6 omega square, and that is your absolute value of magnitude, and phase is arctangent minus arctangent of the 6 omega over 8 minus omega squared. So that should be a typo even from the textbook. So at the end, that is your answer. So when you do plot it, this is how it looks like. Minus 20 dB. Something is happening around between here. And then check where the shift is. I think it's around minus 90 degree, because there was S plus 2 and S plus 4, and it's a second order. This would be in your assessment skill assessment 10.1's solution for like a Nyquist diagram, but we'll be skipping it because we are not covering in this course. And then we'll go into asymptotic approximation and Bode plots.